Hey everyone, my name is Taylor Sparks, and I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation. I'm here to talk about a brand new paper published in our journal, Automatic Detection of Dendritic Microstructure Using Computer Vision Deep Learning Models Trained with Phase Field Simulations. This paper comes to us from Alexander Viardin and co-workers in Germany. Now, one of the interesting things about this paper is that there's been many approaches in using deep learning to identify structures. For example, they point out these papers. There's this crystallographic symmetry for data augmentation, detecting dendrites by Fu and co-workers. Here they use faster RCNN. Or this paper by Akbozo and Jin, where they're using RCNN for similar types of tasks. And there's even my own work in this area by Devanshu, my former student, and myself, where we did the same idea. And how this new article contrasts these is that it is specifically using simulated or synthetic data as opposed to real images, which is a big difference, right? They point out the difficulty that you have to implement if you're going to try and grow these dendrites under these microgravity conditions in the TEM. Yes, it's possible, and yes, you can see these things, but that's a difficult thing to generate experimentally. How much better if you could instead use phase field modeling like the ones they show here to generate all the different types of dendrite structures that you might encounter as you change the different parameters. So they show as you change different conditions, for example, for SCN acetone or aluminum copper, how you can actually generate phase field microstructures that look pretty convincing. And their hypothesis is now going to be, if we only train on these phase field images, if we train our models on those, will they actually be able to carry over to experimental data? So in this paper, they talk about how they generate the data. They talk about the different deep learning models used, specifically faster RCNN and mask RCNN. They point out the ease of this process of generating data, that you're no longer limited by the amount of data available because you can essentially generate unlimited amounts at very low computational cost. And then lastly, they're going to test this on real images, right, and see how it does on actual images for validation. Some of the things they find is that both of these techniques are able to create structures that look very convincing. Furthermore, as you can see, here's an example using faster RCNN. It does an excellent job of finding the dendrites, even when compared to manual annotation. And the same, as you can see here, can be said for mask RCNN. But there are some differences between these two techniques. For example, faster RCNN seems to do a little bit of a better job when these things are overlapping or when there's transparency in the dendrites. On the other hand, mask RCNN seems to do a bit better when they are delineating between closely packed dendritic structures. In both cases, these deep learning approaches are outperforming classical approaches, typical thresholding techniques that might be used. The authors point out the value of relying on synthetic data instead of just experimental data, and obviously talk about how this could extend to other systems and other microstructures. So I hope you're interested and that you'll give it a read.